An important part of measurements is understanding how much we can trust them. And that's something that you'd be reading in the news right now when we're talking about COVID and coming up with cures for COVID. We need to be able to be certain that our measurements have value. And a physicist is always going to report his measurements with the level of uncertainty associated with it, because all measurements have a degree of uncertainty. Okay, even a ruler, when we're looking at a ruler, are we 100% certain that these markings have been calibrated properly? Has that ruler changed over time that made it less accurate? We don't know these things. So we have rules as physicists to apply uncertainties to our measurements so that we can give a level of confidence. All right. Without this, like this guy's saying over here, you may never figure things out. Okay. We'll never have a true understanding of to what degree we know anything without our estimate of uncertainty. So that's a new concept for most of you. We haven't talked about it in grade 10, but in grade 11 and 12, you touch a lot on this in all your sciences to be able to look at a value and understand uncertainty. One thing we need to do when we're doing experiments is minimize our sources of error. So today we're going to try to find out what are the sources of error so that we can talk about it in our experiments and try to design them and remove them. Another thing we want to do is we want to maximize the precision of our measurements and the accuracy. They're not the same thing. You'll learn about that a little bit later on. And then we need to be able to identify when we look at the data whether there was random error or systematic error present in the measurements. Okay, so I know in your reading you've touched on this. This is just a bit of a review. So looking at these rulers, okay, we have inches, we have centimeters. We've seen this picture before. If I'm looking at these, can I trust that this is exactly 16 centimeters? Well, I don't even see a 0 over here. So I don't know if that ruler is starting from the right place. So I would have to say that, okay, according to my measurements, yes, that's 16 centimeters, but plus or minus some type of uncertainty that I would have to say, well, it's probably 16 centimeters. Let me write that down. It's probably 16 centimeters plus or minus, I'm going to say 0.5 centimeters. That's how confident I am. And I didn't pull that out of thin air. That number came to me from a rule. Okay, so this is going to be 16 centimeters plus or minus 0.5 centimeters. And then I would leave feeling pretty confident that I've given a good estimate for the size of that pencil. Okay, about 99% of the time it'll fall in that range. So we're going to learn these rules today. All right, the types of uncertainties in measurement that we are talking about all the way through this course are systematic and random error. And we need to be able to identify them. Systematic errors usually happen and they're applied consistently to all measurements in the experiment. That's how we can identify systematic error. Every measurement has the same shift, all right? And they usually result due to a calibration error or a zeroing error. So if I go back to this ruler, if that was off by 2 millimeters, all my measurements with that ruler would be off by 2 millimeters. So that type of error here would be a systematic error. It's always equally applied. Okay, another common place that we see systematic errors is when students are taking measurements on weigh balances and they forgot to tare or zero the balance. Then all the measurements they're going to do on that balance are going to be off by that value. This is negative 202. Is it possible that an apple is going to be a negative weight? No, somebody forgot to tare it and it wasn't used properly. Okay, so when doing an experiment, you are talking to your friend and you're not paying attention and you forget to look at that. Well, that's okay, because when you graph your results, you will see systematic errors in the graph. Okay, so here are a few different representations of the data. Okay, before the kid did the experiment, he predicted the perfect results using a formula, and that's that black line over here. And in his relationship, the line should go through 0. That's what he said. Okay, so it should go through 0, there's no intercept, and all the dots, it's very linear, okay? And that's the predicted results. And imagine the student got these results. It's very nice, very linear, but they're all shifted upward from where they should be. Well, that is a perfect sign, perfect telltale sign of systematic error, because all the values were shifted by the same amount, and we can see it on the intercept. If you're expecting a 0 intercept and you get an intercept, that is a telltale sign of systematic error. Okay, these dots here, which we're going to learn a bit later, are usually what you'll also see in your experiment, and that's due to random errors, okay, not being precise or accurate in your measurements. We'll talk about that in a second. So often, after the experiment's done, you can go back in your evaluation and you can artificially remove that. You can't say, you have to show that you did that and why you did that. But you can subtract. If I took the data and I subtracted that difference, it would all come down and give me my perfect result. Okay, and you'll be expected to do that after collecting data. All right. Now, random error, on the other hand, is a little bit different. As the name implies, these errors are usually a result of the human observer and a fluctuating environment. It's hard to have the perfect setup. As we know, in Ghana, it's hot. We got air conditioners. We got all these things that you put in your lab reports. Okay, and that is where it'll usually come in. Now, for most of you, the random error comes from our inability to read instruments properly. Okay, and last year you guys told me that when we're measuring water in a graduated cylinder, we need to put it down on a table and we need to look at it level. This is called a meniscus, and I want to look at it level. And that way I can prevent something called parallax. If I'm looking at it from above, my eyes will see the reading being too low. If I'm looking at it below, my eyes will see the reading being too high, the markings being too high. But if I look at it level, I will see the true marking, which is 19.7 at the meniscus. Okay, so you can see quite a drastic range in readings if we're not reading it wrong, and that's called parallax error. Okay, if I'm looking at an analog meter, one way I can make sure that I'm avoiding parallax is if I'm looking at the needle and you see that shadow over there, that means that I'm not looking at it properly. If I see a shadow that is shifted to the right or the left, that means I'm not looking at it properly. I want to look at it so the shadow is directly below the needle. And that way I know I'm level, okay? And right now that reading would be off. You'd probably be looking at that being above 100 if that shadow is shifted to the right, okay? And here's another place where we can get random errors. The student is good. He realizes the ruler is broken, so he takes the block and puts it somewhere in the middle. But when I'm reading this, am I reading those markings correctly? 2.4, maybe my eye slipped and I say 2.3 or 2.5. Or how well can I see that 2.4? I think it's 2.4, but maybe it's 2.42. Okay, so that's just a way of having a problem with reading error. So we can overcome these reading errors by associating uncertainty to my reading to say that we're not perfect. Okay, so when I'm reading that 100, I know there's parallax error involved, so I would say that reading would be 100 plus or minus 0.5. Okay, and that way I know it's half the smallest unit of measurement, and I've accounted for the possibility of parallax error. I can never read that perfectly as 100. All right, so uncertainty of measurement is half, like I just did there, half the smallest unit of measurement for analog devices. And that's how we accommodate for reading error. Okay, so if I'm looking back at this, that's 2.4 centimeters. But if I want to accommodate for reading error, it's going to be half the smallest unit of measurement, which is a millimeter. Okay, so then it would be 2.4 centimeters plus or minus half a millimeter, which is 0.05 centimeters. Oh, 0.05? Yes, half a millimeter. Okay, and then I would change this value to 2.40 centimeters plus or minus 0.05 centimeters because the accuracy of my measurement has to have the same decimal places. All right, now if I can also estimate random error by just looking at the data. If I look at the data that I got for 5 trials of, let's say I'm dropping a ball and measuring the time it takes to hit the ground, all right, if I look at these numbers, they're off. All right, they're not all perfectly aligned. I can say, wow, this 1, 2, 3 values are very, very close. Actually, this student who did this is very, very good because it's very, very close. All right, but then I have 2 values here that are off from the other 3. So the actual value would be my average, like you guys did last year, but let's find the random error. Well, the random error from data is an estimate of my range of the data, and I can get that by finding the maximum value and the minimum value and dividing by 2. Okay, so here my error is going to be, what's the maximum that you see there? 0.582350 minus the minimum, which is 0.582064, okay, divided by 2. And if I calculate that, that'll give me the plus minus value that I would put after the average that I would calculate. And that is my estimate of random error in my experiment. Okay, so in that case, the student did quite a good job of minimizing the random error, probably used a digital meter to measure all that. Okay, and what do random errors look like in graphs? Well, the random errors appear more randomly about the linear distribution. If you're expecting a linear relationship and these numbers are really off from that line, you have a lot of random error in your experiment. So you want to try to get these dots as close to a linear line as possible if you're expecting a linear relationship. If they start to bounce around, then you have things called outliers, okay, or random error. The more spread out they are, the more random error you are, the more likely you weren't paying attention when you're collecting your data. All right, and then the last thing we're going to talk about before the iPad dies here is how I can assess how accurate I collected my data and how precise, okay? And those two don't often go together, okay? Ideally, in an experiment, we want accurate measurements and precise experiments. So let's imagine this is the value. Let's imagine we're trying to measure the acceleration of gravity, which is 9.81 meters per second squared, or better in IB terms is meters per second squared. And I'm trying to measure that, okay? If I did 5 measurements and I got 9.81, okay, that's the bullseye. I'm aiming for that. So I got 9.81. All my measurements are the same. Then in that case, they would all be accurate and precise because the actual value is 9.81 and all my measurements are very close. On the other hand, let's say that I did a bunch of measurements and I found that the acceleration of gravity is 10.2, okay? And in the other 4 experiments, it's 10.19, 10.21, and 10.23. Well, that number is not accurate. 9.81 is accurate, but my measurements are very precise. They all fall in the same range. So in this case, it's not accurate, but all my measurements are precise, which tells me something went wrong in my experiment. I did a good job, but maybe I have systematic error in my experiment, or maybe the tool was not calibrated properly. Okay, here is what happens to a lot of students in the IB, okay, and that's good, is that you end up getting the right result. Your average is around the bullseye, so you'll get an average that is accurate, 9.81, but all the individual measurements are off, so you'll be off by a range. This could be 10.2, this can be 8.8, but if you average it all together, it gives me an accurate, a very close value for G. Again, that's very common for LCS and IB students, that your data looks like that. This is what we don't want at all, okay? So I have imprecise data, and my measurements are all over the place, and when I take the average is way off. In that case, I would say my experiment was a failure, okay? Something is catastrophically wrong in the experiment. So this is the one that you usually have. We're aiming for that, okay? We don't really want that, but we can always go back and try to make it that. Right? In a nutshell, that's our discussion of the different types of errors that we have when we're commonly doing your experiments that you're going to need for all the labs we do in the IA that you're going to write up. And now you know how to identify different types of errors and how to estimate the errors of your measurements.